Yesterday when we were finding limits using graphing software or graphing calculators, I tried to continually express that we're just finding estimates at that point. If we wanted to find the exact value of a limit at a given point, in this case -4, we need to have a more algebraic approach to that. And in this case, we have a rational expression here, and if we're graphing a rational function, oftentimes our eyes are drawn to our denominator, and I do notice that -4 is going to cause some problems with our graph. The graph doesn't exist. That often implies that we have a vertical asymptote and our function is boundless. However, when we put in -4 for a here on a direct substitution, we get -4 to the third plus 64 on -4 plus 4. But this is -4 to the third is -64 plus 64, 0 on 0, which generally implies that we actually have a hole in the graph, in this case at -4. So the other thing that implies, in a rational expression such as this, we have a polynomial over a polynomial. If -4 is a 0, that means that a plus 4 is a factor. In other words, this could be written as limit as a approaches -4 of a plus 4 times something on a plus 4 times, in this case, 1 in the denominator. So the question may be, how do we come up with this guy? And hopefully you note that my numerator is a perfect cube plus a perfect cube, and we have a process for immediately finding the factors of that, one of those apparently being a plus 4. And if we did not, however, we could long divide a plus 4 through our numerator, or we could synthetically divide -4 through our numerator to come up with what's missing. But in this case, I at least know this. First times first equals first. This has to be a squared. Last times last has to equal last. This has to be plus 16. What goes in the middle is the product of these terms for a, and we always have a minus sign somewhere. So again, if you need to long divide that, you'll see that in the next example. Now, I notice I have common factors, and now if I direct substitute -4 into what's left, I get -4 squared minus 4 times -4 plus 16, or 16. This turns out to be plus 16 plus 16 for 48. So one of the strategies, if we have a rational function, a polynomial divided by a polynomial, and it turns into a 0 on 0 upon direct substitution, it's factorable. And when we cancel those factors, good things tend to happen. Let's take a look at another problem similar to that, and I'll actually go through long division and synthetic division. Okay, so here, our direct substitution on this problem gives us 2 to the third plus 2 times 2 squared minus 5 times 2 minus 6 on 2 to the third minus 7 times 2 plus 6. And you can do the arithmetic on this. Take a quick peek at it. You will end up with 0 on 0. So there's a lot going on here, and I'm looking at this numerator and thinking, boy, I'd like to be able to factor that. Upon inspection, it does not look like a breeze to do this by grouping, and the denominator is almost more intimidating for factoring, but I do know this. I do know that this is going to be a limit. I do know that x minus 2 must be a factor. And therefore, if x minus 2 is a factor, I have two options. One of those is to take x minus 2 and long divide it. I'm going to do that with the numerator. Here's an option. And in long division, I'm just going to check how many times x goes into my first term, x cubed. Let's get that arrow out of the way here. Okay. X goes into x cubed, x squared times. And I get x cubed minus 2 times x minus 2x squared. But don't forget we are subtracting these guys. So I end up with 4x squared, bring down the minus 5x. X goes into 4x, 4x squared, 4x times. So plus 4x gives me 4x squared minus 8x. But once again, important not to forget we are subtracting these. And we end up with 3x minus 6. X goes into 3x 3 times, and that gives us 3x minus 6, so it worked out perfectly. That should come as no surprise. So right now, I could rewrite the numerator of my limit. Limit as x approaches 2. I could write that as x minus 2 times x squared plus 4x plus 3. My other option is to synthetically divide. I'll do that in the denominator. I could just synthetically divide 2 through 1x cubed, 0x squareds, negative 7x's, and a constant of 6. And I get 1 and 2 times 1 and 0 and 2 and 2 times 2 and negative 7 and 4 and 2 times negative 3, negative 6, and holy cow, it worked. Well, we should expect it to work, which means my denominator could factor into x minus 2 and 1x squared plus 2 x's minus a constant of 3. And at that point, I can cancel the x minus 2's, which gives 2 a chance that maybe it's not going to produce 0 on 0 as we substitute it in directly now. Now, if it did produce 0 on 0, then we could further divide this down. We could further factor this. You may notice we can further factor the quadratics that are left here perhaps, but I don't think it's going to be necessary. As I direct substitute 2 into this, I get 2 squared plus 4 times 2 plus 3 on 2 squared plus, that's not 4 squared, that's, I'm sorry, 4 times 2. 2 squared plus 2 times 2 minus 3 in the denominator. And I end up with in the numerator 4 and 8, 12, and 3, 15. In the denominator 4 and 4, 8, minus 3, 5, for a nice clean limit of 3. So those are two examples of when you have polynomials. I think probably most people, given the option here, might want to choose the synthetic, which would always be an option in these problems. Okay. Then we're going to talk about a couple more problems where I guess I'm just going to refer to it as we have a mess and we look at this function. I don't really know what the graph looks like. I do know that weird things are going to be happening around 2. My first thought is maybe we should try direct substitution, which would get us to 4 minus root 18 minus 2 on 2 minus 2, and unfortunately that is 0 on 0. We're crossing the beam. So I need to try to clean this thing up algebraically. I wish I could go to technology, but what if I have to know the exact value? So what could I do with this 4 minus root 18 minus x on x minus 2? Well, the messiest part of this, in my eyes, is our radical in the numerator. And if I wanted to get rid of that, I could use a conjugate, 4 plus root 18 minus x. Unfortunately, that means I'd have to multiply the bottom by 4 plus root 18 minus x. But sometimes just changing the form is helpful. And this is going to end up being one of those times. So as I FOIL the numerator, I get a 16. I'm going to get 4 of the mess, but minus 4 of the mess. That's conjugate work for us. And I'm going to get a minus, careful here, minus times plus minus all of plain old 18 minus x. Those parentheses are pretty important. I'm not going to FOIL out the denominator. You'll see why shortly. X minus 2 needs to be multiplied to 4 plus root 18 minus x. So careful to distribute the numerator, or the negative in the numerator. I end up with a positive x and a 16 minus 18 minus 2 in the numerator on x minus 2 times 4 plus root 18 minus x. And I think you're seeing the payoff here. This again is the limit as x approaches 2, and we can now clearly see why putting a 2 in there gave us some problems. But if those cancel, it's worth giving 2 another shot, direct substitution. So we end up with 1 on 4 plus square root of 18 minus direct substitute 2 in, and we get 1 on 4 plus square root of 16, 4 plus 4, 8. So I guess a nice rule of thumb is if you see a mess, just try to work with the mess. Try to clean up the mess. In this case, trying to clean up that guy ended up helping us out. We're always looking to try to cancel the troublemaker, so I was trying to find factors of x minus 2, and that is why I never foiled that guy out at that point. I want to have a factor of x minus 2 to cancel. I was fortunate enough to come up with one. So we learned to look for our messes. And right here, I certainly see a mess in that we have compound fractions, but let's go ahead and give direct substitution a try. I put in 0, and I get 1 on 0 minus 8 plus 1 on 8, all on 0, which is negative 1/8, plus 1/8, 0 on 0. I expect there to be a hole in the graph. So I need to clean this thing up. I need to do something about this, and I notice that this is compound fractions. I think everybody would notice that and be repelled by that. So let's do something about it. What I do about this, and there's a lot of ways to get rid of the compound fraction, but I look at my 3 terms, 1 term, 2 terms, 3 terms, and I look for my least common denominator out of those, and that includes a factor of 8 and a factor of x minus 8. I'm going to multiply top and bottom of the fraction by x minus 8, or multiply by 1. Okay. So my numerator, when I distribute this whole package, think of this as a whole package, to the first term, the x minus 8's cancel, and I just get 8 times 1. Then I have a plus. When I distribute to the second, the 8's cancel, and I get 1 times x minus 8. In the denominator, I'm not going to distribute or FOIL because I'm really interested, if you paid attention on the last slide, I'm really interested in canceling that x at some time. So I'm going to leave my denominator as 8 times x times x minus 8, and don't you dare think about canceling those x minus 8's now, because this guy is just a term, and we don't cancel terms. But I can take the numerator, do a little simplifying. 8 plus x minus 8 just gives me the x that I'm really looking for. On 8x times x minus 8, I am trying to find a limit as x approaches 0. This, being the troublemaker, is now canceled. And now let's try direct substitution. Direct substituting in 0, I get 1 on 8 times 0 minus 8, or 1 on negative 64 for negative 1/64. Okay, and here is really kind of the ultimate goal of this, is to move into this is going to be a study in calculus. A lot of times there's a Latin phrase called that is ad nauseum, which is just about what it sounds like. It's until you're sick of it. There is a chance you will be doing so much of this work over the next year. This will be an ad nauseum situation for you. But for whatever reason, this causes some confusions for us, and it shouldn't. When I view that, I'm just saying I am driving x plus h into a factory that works on cars called F. I wonder what f does. I wonder what this f factory does. Well, here the f factory is defined, and it says if you drive something in here, we're going to attach a 6 to it, and we're going to subtract that result from 5. So whatever gets driven in the factory goes right here. So what is f of x plus h? If I'm driving x plus h into the factory, it goes right there. It is 5 minus 6 times x plus h. So let's piece this together. I want to put this guy in place of this. So f of x plus h is 5 minus 6 times x plus h. And then I want to subtract f of x. But I'm subtracting all of f of x, which is 5 minus 6x. And I'm putting that on plain old h, trying to find the limit as h approaches 0. Well, I got some pretty easy algebra to work with on the numerator here. So I get 5 distribute minus 6x minus 6h, distribute the negative minus 5 plus 6x all on h. We're looking for the limit as h approaches 0. And what good happens in the numerator? I've got a 5 minus a 5. I've got a minus 6x plus a 6x. So I'm now trying to find the limit as h approaches 0 of negative 6h on h. And I notice, well, I can't put 0 in there. I get 0 on 0. But we can factor out or cancel out h's. And I'm finding the limit as h gets close to 0 of negative 6. And there's no place to put my 0 in there. There are no h's in this. So this is just negative 6. Now we're going to have some discussions in the coming days on why it should not be a surprise that if I look at f of x in a cleaner perspective, shouldn't be any surprise at all to us that this formula leads us to the slope of that line.